Ladies and gentlemen, this talk will be about structural quantities. Structural quantities, as the name suggests, tell us or quantify the structure of liquids or solids and so on. There are two important types. First, the correlation functions. The correlation functions describe a correlation, that is a relation between 2 points in space or 2 molecules, typically some space or perhaps time apart. The most important one, I will speak about it in detail, is the radial distribution function. It is a normalized probability that I find a particle a certain distance from another particle, and it is normalized in such a way that ideal gas has unity. Closely related to this function is the structure factor. It is, simply speaking, what I get from a diffraction experiment. Then we have different types of angular correlations and also time correlation functions. The second type are order parameters. These are functions. Order parameters are numbers. The simplest example is just average cosine of angle. I mean the theta angle is the angle from the z-axis. It distinguishes molecules which point up, then the cosine is unity, and down, then it is minus unity, and there are cases in between. That is, it tells us whether the liquid, maybe a dipolar liquid for example, is ordered or is not ordered in certain direction, which I specify at start. If I want to distinguish whether certain, let us say, symmetric molecules, you can imagine carbon dioxide for example, point up or down, that or with the axis in parallel to certain direction, let us say z, or they lie perpendicular to it, then this type is suitable. Then we have formulas which can detect different local order. As an example, imagine ice. Here is a very small piece of ice structure, and each water molecule is surrounded by 4 water molecules or 4 oxygens which are arranged tetrahedrally. And there exists a formula, I am not going to provide it here, which detects this. That is, I choose an oxygen atom, I find 4 neighbors, and then put positions of these neighbors to this formula, or perhaps only angles, and the number tells me whether there is a tetrahedral arrangement around the central atom or whether it deviates in some way from this. This quantity can be used, for example, to detect crystallization or just to study the structure of water or molten silica or something like this. To understand the pair correlation function, let's first imagine ideal gas. We have n molecules which freely move through a box. The question is, what is the probability that I find a molecule, any of these n molecules, within a small cube of volume dV? The probability is the number of molecules and the ratio of both volumes. I can change my perspective a bit, and my question will be, what is the probability of finding such a molecule provided that I have 1 molecule fixed? And then my question is whether there is a deviation of this probability with certain distance r from this point. Of course, it is not for ideal gas, but it will be for real fluid or perhaps solid, simply matter where there are correlations. In this case, I introduce a correcting factor, which is called the pair correlation function, also radial distribution function. That is, the probability of finding a particle, one of n, could be n minus 1, but I assume I have many particles, so it doesn't matter. To find such a particle r apart from one chosen particle is given. This value, which is the same as for ideal gas, and this correction factor. And this correction factor is called the radial distribution function. From this, what I've said, it follows that for pure ideal gas, the radial distribution function is unity. This is my standard. What about such a simple liquid like liquid argon? Here there is the experimental radial distribution function for liquid argon, and what we can see is that it is 0 at very small distances. That's because I cannot smash two argon atoms together because they repel each other a lot at very short distances. But if there is one atom somewhere, one chosen, then the atoms which are around have a tendency to be organized in a shell. It's not a very well-defined shell because molecules in a liquid constantly move there and back. But a sort of high probability that you can find a particle here. And this is represented here by this peak. And this peak typically is about 3. It means that I have 3 times higher probability that I find a particle from a chosen particle, any chosen particle in liquid argon at this distance. And this distance corresponds at normal pressures to the potential minimum, because then molecules have higher probability that you will find them. Okay, so this is the first shell. When I go with a distance further, let us say to 1.5 this nearest neighbor distance, then the liquid is depleted, but not fully. With some probability I can find a molecule with distance 1.5 of the nearest neighbor, but it's less, because the first shell doesn't allow other molecules to be easily incorporated at this distance corresponding to 1.5. Typically this may be about 1/2, half the probability. And for the same reason, why there is a shell of first neighbors around a molecule, then there is a shell of the second neighbors, but the second shell is not so well pronounced. That is, here I have a higher probability, let us say by 20 or 30%. And I have the second region where the probability is lower, and the third maximum, and so on. And these oscillations exponentially decay in a liquid. That is, liquid argon has a structure which is organized in shells around any chosen molecule at a statistical interpretation, of course. So you can find a molecule which is surrounded by something else strange, but with a low probability. Of course, we can calculate this radial distribution function in simulation, but we can also measure it. To obtain this experimentally, we need suitable radiation. The best ones are neutrons, but they are the most expensive to do, to make neutron rays with precise wavelengths. An easier way, and most often used, are X-rays. Sometimes also electrons are used. Then I have a sample of matter, it may be crystal or liquid, which was the case I showed you on the last slide. And this radiation goes through a sample and it scatters into such a typical pattern. If I express this pattern mathematically, it's called the structure factor. And I can reconstruct from this structure factor the radial distribution function by something that is called the inverse Fourier transform. I am not going to cover mathematical details about this inverse Fourier transform. You can imagine that it is something that people with good musicians are able to do. They can hear sound from an orchestra and distinguish individual tones. So this reconstruction of tones is the Fourier transform, and I can do it in both directions. I will put on YouTube an experiment which uses a laser pointer. A laser pointer and such a pattern, several types of patterns. And laser pointer is a coherent radiation. It's made of light, of course. There are no neutrons, no X-rays, but also these patterns are wider than the interatomic distances. They were printed on a sheet, and after diffracting through these patterns, I am getting the structure factors. Here below they are calculated, but on a YouTube movie you will see this as an experiment. Okay, so to summarize and to show some other examples. Simple liquids like liquid argon are organized by shells. This highest peak on the radial distribution function corresponds to the first shell, where there is the highest probability that I find another argon atom in comparison with ideal gas, about 3 times. In the case of hard spheres, it's a bit similar to liquid argon. These are spheres or spherical objects. So the radial distribution function is similar, but because of the discrete nature of hard spheres, the peak here is such a point-like. But what's interesting is to look at water. What you can see here is the radial distribution function oxygen-oxygen between two water molecules. At a short distance there are no molecules, of course, and there is the first peak. In water, the leading interaction is a hydrogen bond interaction. So that this first peak corresponds to a pair of water molecules with a hydrogen bond, that is, with an atom of hydrogen in between. Then we have a minimum. But the second peak is not at twice the original distance, or twice the distance of the first shell as for liquid argon, but it's at a bit shorter distance. And that's because water structure is different from the structure of liquid argon. The second neighbor here is controlled by 2 hydrogen bonds. They correspond to a tetrahedral arrangement of 2 water molecules around 1 water molecule. That is, this dotted distance is quite probable. But because of the geometry, it doesn't occur at twice this oxygen-oxygen distance, but shorter, and it's about 0.6. It corresponds to a tetrahedron. You can calculate it. And for all liquids, fluids, the structure decays to unity, or the correlations decay to 0. There is another quantity which is, I would say, a bit easier to analyze. It is the cumulative radial distribution function. also called the running coordination number. And why the coordination number? First, let's rho denotes the so-called number density. It is the number of molecules in volume. And here I have an integral. The integral is over the element 4 pi times squared radius times dr. If I draw it, it means that I have a sphere around the central atom. This distance is r or r bar here, and I can imagine a tiny, very thin shell of dr here. Then the volume of this shell here equals 4 pi, it is, or 4 pi times r squared is the area of the sphere, and times dr is the volume. That is, the blue volume here is given by 4 pi r squared dr. And if I multiply this by the number density, I'll get the average or expected number of molecules. This would be for ideal gas, but of course I have the radial distribution function here, so I'm getting the true number of molecules. And if I integrate over such shells up to certain distance r, what I am getting is the average number of molecules which are at most r apart from the central molecule. And it's called the coordination number. And because I have a function, it's called the running coordination number. Here there are radial distribution functions of a model of water. It's not real water. I guess this is the SPCE water, but it's not important. The qualitatively it shows the same. And I have here two types of radial distribution functions and running coordination numbers. This blue dotted line shows the radial distribution function oxygen-oxygen. It is pretty similar to what was shown before. That is the first peak corresponding to hydrogen bonding, and the second peak which is at a shorter distance than twice the first peak. And from this function I calculated the running coordination number. It is here, and you can see an inflection point somewhere here where there is a minimum here, and this inflection point shows us the number of neighbors. Here it is about 4 or a bit more than 4 even. Typically, if I use a better model, it will be rather a bit less than 4, but it's around 4 anyway. The problems are caused, or problems in interpretation are caused by the fact that this minimum is not so well pronounced. But for the radial distribution function of hydrogen and oxygen, I am getting a bit different or a bit clearer picture. Again, this distance corresponds to the hydrogen bond. That is a hydrogen which is close to oxygen. It should be noted that I only show here the intermolecular hydrogen and oxygen interactions or distribution function. If one wants to include the intramolecular, there would be a peak at about 1 angstrom here, because it's a distance of intramolecular function, so that but it would be very sharp peak, just vibrating. But it's in this model it's not usual to include intramolecular interactions or intramolecular distribution function. Okay, so I have this peak, which corresponds to the hydrogen bond. Then there is very deep minimum, meaning that it's very improbable that I will have a hydrogen and oxygen about 2.4 angstrom apart. But it also gives a very pronounced inflection point or plateau here on the running coordination number. And it means that this plateau will show me quite well how many neighbors I have around an oxygen molecule. In this case, in the calculation of the cumulative distribution function, because of the number density of different atoms, it's not the same if I calculate hydrogens around oxygens. I can calculate also oxygens around hydrogens. It will be 1/2. Here there are hydrogens around oxygens. Of course, this distribution function is the same irrespective of the order, but not the running coordination number. So this is for hydrogens around oxygens. And here I have the average number of hydrogens which are hydrogen bonded to an oxygen is about 1.9. It is almost 2. It means that almost all water molecules are hydrogen bonded essentially 4 times, because there are 4 neighbors. Okay, some of them are not bonded. Once a while there is a molecule off, but this is how liquid water works. If I showed here the radial distribution function for a crystal of ice, I would get essentially 2 with several decimal digits here. Okay, I showed you approximately how to get the radial distribution function from a real experiment. I am using X-ray scattering or neutron scattering, and from the structure factor I calculate the radial distribution function. It's not easy if I have many types of atoms. So for example, argon, I have only one type of function, but in water I have 3 types of functions. So I must use isotopes, for example, in a Newton diffraction to be able to separate different terms and combine different diffractions and so on. So it's not so easy for mixtures and for complex substances, but the principle is that I use diffraction and the inverse Fourier transform. In simulation, the calculation is simple because I know positions of all particles. I will explain you the principle for a simple fluid, just one type of particle for simplicity. Usually this radial distribution function is calculated using a histogram of the number of particle pairs which are at certain distance. So I am running a simulation. I am taking all pairs of particles. For each pair of particles I calculate the distance. The distance, let us say r, and I have the distance split into several bins which are thick delta r and I the subscript or index. So if I get a hit, that is the distance I have goes to this histogram, I accumulate unity into this histogram, and I do this for the whole simulation, and during the simulation I do it again and again to get good statistic over many configurations. This is the interval, or I can use this type of interval. There's no principal difference between these two. So to calculate the radial distribution function, I need to know what's the volume of this shell. And this volume of this shell, that is of distances in this interval, is given by the difference between the volume of the bigger sphere minus the volume of the small sphere, and the radii are here. It is for this case. So this is the volume. And then I accumulate the number of particles, which is denoted here is the script n with subscript I in this interval. And I know that in the case of ideal gas, the number of the expected number of molecules in such a volume is the number density times this volume. This would be the ideal gas. However, I am doing a sum over all particles. So in this procedure I would get the same contribution twice, because to be a pair is a pair quantity. So that for ideal gas, by the procedure that is described here, taking all pairs, what I get in this bin with subscript I, that is corresponding to this interval, is 1/2 of this. That is n½ times the number density times the volume. So this assumes that I ran a double loop over the system, that is over all pairs, and there are n over 2 pairs in the system. Okay, and the radial distribution function is what I have accumulated on average divided by this expected value for ideal gas. This is the correcting factor. So this is the final formula. And now I will show you how this works with simulant. You already know it, and your homework will be to try all this by yourself. Now I will show you the radial distribution functions of a gas, liquid and crystal in 2 dimensions using simulant. I recommend that you install simulant and try it by yourself. So let's start simulant, and so that I can see now the guide. First we will need, or it's better see more accurate, using the periodic boundary conditions. So I set up them. Then, because of crystal later, I will choose the magic number of particles, measurement block to maximum, because then it will be calculated not so often but with a higher precision. And now we can play with density, for example. Now you can see the radial distribution function of gas, of real gas, which is not so dilute. There is one maximum, and here there is unity. The function is always scaled from minimum, which is 0, to maximum, that is unity is somewhere here. If I decrease density, there will be less structure, but still the first maximum is preserved because it's given by the attraction. If I increase temperature, then the first maximum will not be so pronounced. So I decrease it a bit, and here the attraction slowly prevails, but still I have gas. Okay, so let's go somewhere in between. And now I will increase the density. It looks like I am increasing the size of particles, but actually I am decreasing the box, and I'm showing it as the box has the same volume. That is, this means that I'm decreasing volume and showing in the same area on the screen. Still, the radial distribution function looks similar, but here, as the liquid gets denser, we can see the first minimum. And with a higher density, the structure, the shell structure, already develops. So let's continue with increasing density. And the higher density, the more pronounced structure. Okay, so let's play with temperature. If I have a higher temperature, this structure is not so pronounced, but just a bit. So let's try decrease temperature slowly. Again, the structure is more and more pronounced, and I will do another trick. That is, I will show in color the number of neighbors. Actually, it is the coordination number up to the neighbor limit, which you can see here. So here still there is something irregular, and if I go with temperature below, it looks like that there are two defects in the structure. So this crystal is not so perfect, but the number 209 means that there exists a case where it should crystallize without any defect, but it needs to be a bit patient here. Yeah, and I guess it is perfect crystal or almost perfect crystal, and you can see that the radial distribution function now consists of peaks which are very high, and it is not liquid anymore, so there is no limit unity. It would be at very long distances anyway, but it's not here. Still, I can add a bit more heat into the system, so the system fluctuates more and these peaks are wider. But if I decrease temperature, I am getting very narrow peaks. You can see a print screen of this radial distribution function here. And what is the interpretation? Of course, R1, the closest distance, corresponds to the nearest neighbors. The distance is a bit more than 1 for given density, because 1 corresponds to the size of these disks. Then I have a second neighbor somewhere here. So this is the second neighbor, R2, and it corresponds to this distance in the lattice. And the third one is apparently twice the first one, because R3 corresponds to this arrow. There are two atomic diameters. So apparently R3 divided by R1, this by this, is 2. And your homework will be what is theoretically in this lattice the ratio of R2 to R1. Okay? And then you can check whether it really is detected correctly. So thank you for your attention for today.